Bunty and Daniel Mars, and all this happened when I was a postdoc or towards the end of the postdoc, and it's kind of on the basis of two papers, but I will talk about one of the papers in more detail. Okay, so I'm going to talk about Group Steiner Tree problems, but before going into Group Steiner trees, let's just begin with the Steiner tree problem on a graph. Okay, so here is the setting. I have a graph, and I have some cost on my edges, let's say. So it's a weighted graph. And in addition, I am given a bunch of terminals. So let's say the orange vertices, they denote the terminals in my graph. And the blue vertices, which I call Steiner vertices, they are not terminals. They are non-terminals. Okay? And the task for me is to find a subgraph out of this graph, which keeps these orange vertices connected with each other, okay, at the cheapest possible cost. So that's the basic Steiner tree problem. It's a very classical problem in combinatorial optimization. Many of you might be already familiar with the problem. Yeah, and note that it's only required that the final subgraph connects the orange guys. I don't care how many blue guys I take, okay, but taking some of them might be beneficial in order to reduce the cost of the solution, okay. And also another thing to note is, why do I call this a Steiner tree problem? Because the optimal solution will always be a tree. There is no point keeping a cycle in the graph, right? Because all I care about is connectivity of the orange vertices. Yeah. So, in fact, if all the vertices are orange, then what we have is the familiar minimum spanning tree problem, which we know can be solved in polynomial time very efficiently. However, by the way, so that's an example of a Steiner tree in this graph, right? So if I take the red edges, then they connect the orange guys to each other. So there is a path between every pair of orange vertices. Yeah. Okay, so it turns out that the Steiner tree problem is very hard. So we cannot hope to solve this exactly in polynomial time. And so what we do is our one of the usual notions of resorting to an approximation algorithms. So just for sake of completeness, what is an approximation algorithm? Well, I know that if I want opt, then I have a super polynomial running time. So what I shoot for instead is a solution that is slightly worse than opt, but I really give you guarantee that it won't never be worse than alpha, yeah, for some alpha. But the algorithm will run in polynomial time in the size of the input. Okay, so that's the Steiner tree problem. But remember, I had a group prefix at the title of my talk. So let's now switch to the Group Steiner Tree problem. So the setting is very similar. Again, I have a weighted graph. I removed the weight just to make the figure cleaner. But now, again, I have a bunch of terminals. But now I give a color class to each of the terminals. Okay? And in fact, it's not a partition. A specific terminal can belong to more than one color class as well. Okay? And let's call each of the color class a group. Each color class, I just call it a group. Yeah? It's a group of terminals. And in addition, let me also introduce a root vertex in my graph. So this problem can also be defined without the notion of a root vertex, but just to keep the definition cleaner and simpler, let's stick to this version. Okay, it's a rooted Group Steiner tree problem if you want. And now the question is almost the same as the Steiner tree problem, with this one exception that now I want at least one terminal from each color class to be part of my final subgraph. Okay? So let's say I want to connect at least one orange vertex to the root, at least one green vertex to the root, and at least one red vertex to the root. Okay? I don't have to connect all of them to the root, which was the case for Steiner tree. So Steiner tree is a special case of this problem where each terminal forms a color class of itself. Right? So then it just becomes the standard Steiner tree problem. Okay. So any questions about the problem definition so far? So that's an example of a Group Steiner tree. So if you check the connections, you will note that I have indeed connected every color class to this root. Yeah? So there's a path from, let's say, the root to an orange guy and the root to a green guy and so on. Yeah?
These are usually on undirected graphs?
Yeah, I don't know if anybody has looked at, because directed Steiner tree is already hard, and directed Steiner tree actually captures this problem as well.
Yes, that's what I thought you could create one single
Yes.
each right vertex.
Exactly. Exactly. So directed Steiner tree it generalizes this problem. Yeah. But I don't know if somebody has looked at directed Group Steiner tree. I have to check the literature.
But in this example, you have taken this red and this color all together.
This one? Yes.
Again, you are adding that one. So is it mistake?
Oh, that's correct. That's right. This is not an optimal solution. You are right. I could only do away with this part of the tree. Absolutely. Yeah. You are right. Okay. So this was just to show you that one terminal can belong to two color classes. So it's enough. Yeah, that's right. Okay. So let's take a walk through what is known about the approximability of this problem. So it turns out that this problem is much harder compared to Steiner trees. So Halperin and Krautgamer, they showed in 2002 that its log square h hard, its NP hard to approximate it beyond a factor of log square h, where h is the total number of groups in my input. Yeah, so it's h is the total. So n is the total number of nodes, but h is the total number of groups. So they showed that it's log square h hard. In fact, it's log square h hard even if the input graph is just a tree. So remember, I have to extract a subtree out of my input tree. So even in those instances, this problem is log square h hard. Yeah. In fact, I think it's a nice exercise to show. So we heard about the set cover problem this morning. You can reduce the set cover problem to this problem if you consider a star graph. So the hardness of set cover already carries over to Group Steiner trees, but they showed that it's actually even harder. So there's a log square h hardness. Okay. So that's the lower bound. On the positive side, so this was a culmination of essentially two different results spanning over 5 years. So there's a log square n log h approximation algorithm known. So again, n is the number of nodes in my input graph, and h is the total number of groups. So that's on the positive side. So we will talk about this result in a bit more detail in a few more slides. So what else is known is the following. There is a matching upper bound known, matching upper bound of log square h. So this was a result by Chandra Chekuri and Martin Pal back from 2005. But this algorithm, it runs in time n to the power of order of log n. So this is a quasi-polynomial time algorithm. It's not a polynomial time algorithm. And in fact, this algorithm works even for the directed Steiner tree problem, which, as I said, is a further generalization of Group Steiner trees. Okay. So I would like to mention another very strong positive result, and this is the strongest positive result known for Group Steiner trees on any class of graphs. So consider that the input graph is planar. Okay, so I know that I cannot do much for general planar graphs. Why? Because this hardness holds even in the case of tree graphs. But if it happens that your graph is planar and every group is completely contained in a disjoint face of the planar graph, if the input happens to be like that, then in fact they showed a polynomial time approximation scheme for this problem. Okay? And why is this setting important? Because this problem was sort of motivated by electrical circuits, and it turns out that this notion of restricting the groups to the face of the graph, it actually applies to those kind of applications. So this result was so other than the techniques, they were pretty sophisticated. That's of course important, but it's also well motivated in practicals. So that's kind of the picture that is known so far. So when do we chip in? Well, we show a log n times log h approximation for another special class of graph, which are graphs of bounded Treewidth. Okay, so bear with me for a few slides. I will introduce for what bounded Treewidth is, at least at a high level. But they are graphs which are more general than trees, but they capture a wide class of graphs and they are interesting in their own rights. So for graphs which have a constant tree width, we show a polynomial time algorithm that gives a log n times log h approximation. So that almost matches the lower bound that is known. Okay. Any questions about the result itself? Alright. So let's take a step back and let's look at what's the usual technique that is used in literature for solving this problem. So the first step in general is the following. So what I do is, so let's say this is my input graph, yeah, and now I make another further assumption that the edges in my graph, so I have not shown you the complete graph, but assume this is a complete graph, or assume a metric completion of this graph if you want. So I'm assuming that my input graph is a metric. Each edge, the edge lengths, they follow triangle inequality. So let's say I'm given this input graph. Then there is this seminal result by Bhatt back from 99, and it was later on made tight by these three authors in 2003, which shows that you can essentially embed this graph into a tree kind of structure, even into a tree. It's exactly a tree, but it's a probabilistic tree. So you give a distribution of trees such that the distances between any two nodes is preserved up to a factor of log n. Okay, so this is also known as the distortion of the metric. So you are given an input metric, from that you create this tree metric, and now you look at the distance between, okay, the leaves correspond to the vertices in the original graph, and the distance between, let's say if I consider the distance between these two red vertices in the tree, then the length of, then the total length of this path in expectation is at most log n times the total length of the path in the original graph. Okay, so that was a very important result, and in fact it is still used very widely to prove polylog approximations for many problems which are hard, because now what we have is a somewhat easier problem. We just need to solve the problem on the trees. Yeah, we have essentially reduced the problem from a general graph to a problem on the trees, and then we use this result back from 98 that was by Garg, Konchimon and Ravi, who showed a log n times log h approximation to solve the problem on tree graphs. Okay, so now if I combine these two loss in approximation factors, what I have is a log square n times log h approximation for the original. Okay. Any questions about? Yeah. So that's a pretty standard way in what people usually approach the Group Steiner problem. Although I must say here that, remember I also showed this result of log square h upper bound, which runs in quasi-polynomial time, that avoids this embedding. That actually works directly on the input graph, because remember it also works for directed Steiner trees. So for directed graphs, this kind of embedding does not work, or at least it's not known. So that's just a greedy algorithm that it works on the input graph itself. But all other Group Steiner problems essentially first embed it into a tree with the log n loss, and then just solve the problem on the tree. Okay. Now remember, I am shooting for a factor which is log n times log h, let's say. So that's the open question, right? Now, what is the first bottleneck that I hit? Well, the problem is already log square hard on trees themselves. So I cannot hope to improve this factor by a lot. The best I could possibly do is improve this to log square h, but yeah, that's not a great deal of improvement. On the other hand, the question is then, can I improve on this factor? Is there a hope there? But it turns out that's also not possible. So there are instances where at least this kind of embedding, it has a lower bound, distortion lower bound of log n, even for graphs which have low tree widths. Okay, even for graphs of tree width 2, there are instances where you will have to incur a distortion of log n. Okay, so any algorithm that tries to take this approach is bound to sort of hit this log cube barrier in some sense. Yeah. So the question is, how do I now break this log cube barrier? Is there any hope of avoiding this kind of embedding at all? Okay. So that's what we try to answer, and what we showed is a different notion of an embedding, which I will talk to in more detail in a few slides. And what we showed is that we can use a similar notion of embedding, but now I am not going to embed the metric onto a tree. I am essentially going to embed the different optimal solutions into a tree and then solve the problem on the tree graph. More on that later. But the important thing is that now I embed it into a tree, but the size of this tree blows up a lot. So the size of the tree turns out to be w times log w, where w is the tree width of the graph. Okay? So as long as w is a constant, this is a polynomial time algorithm. Yeah? But another important notion is I do not have any loss in this process. So remember here I lost a factor of log n, and this is what I will always use. But in our embedding, we essentially avoid that loss. And we will try to see how. Yes.
That requires the graph to be followed that metric property.
Okay, so the result is much more general. It says that given any metric, you can embed a metric into a tree. Like any graph metric, you can embed it into a tree such that this distortion is order log n expectation.
So it has to follow triangle.
The input graph. Okay, so let me keep it at this, that you can assume without loss of generality that there is a metric completion. If it's not, what you can do is you can complete the graph by taking the shortest path between any 2 points. And then once you solve the problem on this metric, you can just map it backwards. So it's without loss of generality. Any further questions? So, okay, so let me, so in order to motivate this sort of embedding, I need to take a detour and introduce you to the notion of tree decomposition and tree width. I will not go into too much detail, but just, highlight the properties which I need out of this thing. So what is a tree decomposition? Well, let's say I'm given this graph, and what I do is I generate a tree which is as follows. So each node of this tree corresponds to a subset of the nodes in my original graph. Yeah? And then of course I have to connect these nodes with some edges such that it becomes a tree. But these connections have to follow some properties. By the way, these nodes are also popularly known as bags, just to differentiate them from the nodes of the original graph. Okay? So each of these nodes, they contain a subset of the vertices of the original graph. And there might be intersections. It's not a partition. Okay? I mean, one vertex can be part of several bags in the decomposition. So what are the properties that I want? The first property is that if I look at any edge in my original graph, then this has to occur in at least one of the bags in the tree decomposition. Okay? That's property number one. For instance, the green guy appears here and here. And let's say the purple one, it appears here as well as there. Yeah? So that's the first property. And the second property, which I find more interesting, is the following, that if I look at all the bags that contain a specific vertex, then they form a connected subtree in my tree decomposition. Okay? So they have to essentially form a subtree in my tree decomposition. Yeah? So it can't be that some of these bags are lying at the top and some of them are lying at the bottom and there are other bags in between. No. Then each of these other bags must also contain this particular vertex. Okay? So if I look at this example, then this red guy, it appears in all these 4 bags, and so in the tree decomposition, I have kept them connected via this path. Yeah? It does not have to be a path, it could be any subtree, but they have to be a connected sort of subtree in the whole tree decomposition. Okay? So if these 2 properties are satisfied, then what we have is a tree decomposition. Now, and once we have this tree decomposition, let's assume that we have such a decomposition. Let's say it's possible to do this. Then I can define the notion of the width of this decomposition, which is the maximum size of any bag minus a 1. Okay? So now if you think about it, if I give you a tree, that is a tree width of 1. Yeah? Because you can just keep every edge in every bag. So yeah, it's essentially just 2 minus 1, which is a 1. So a tree is a graph of tree width 1, for example. Okay? Any questions about the definition? I know it's a bit weird if you're saying this for the first time, but I will just tell you another property which I will use, and you can forget about the rest.
So, in the decomposition graph, is there a restriction on the edges, or just that they should be connected?
That's the restriction, right? I mean, what I said already imposes some restriction. So, yeah.
I mean, can't you not just make a complete graph of bags, maybe?
Oh, that's not a tree, right?
Okay.
Yeah. Okay. Any more questions? Right. Okay, so yeah. So now the question is, what is the tree width of a graph? Well, it seems like it's an inherent property. Well, indeed it is. Well, remember the width of I have defined the width in terms of a given tree decomposition, and now I ask the question, what is the best I can do? Which is the tree decomposition that gives me the minimum width of any bag? Yeah? And that is defined as the tree width of the graph itself. So it turns out that finding, if the tree width is part of the input, then finding such a decomposition is NP hard, but there is a very efficient fixed parameter tractable algorithm. So I'm not going to detail of all that. Actually, it runs in linear time. So for constant tree width, there's a linear time algorithm which can give you this tree decomposition. Okay? In fact, I'm also going to assume something more. I'm going to assume that I have a nice tree decomposition of my graph. So what is a nice tree decomposition? Well, it's essentially that the tree decomposition is a binary tree. Okay? So this is also possible, but then you have to blow up the size of your bag by a constant factor. So if the tree width of a graph is, let's say, k, then you can have a nice tree decomposition which has, let's say, the size of each bag is 4 times k. So I only lose a constant factor if I assume this nice property. But I'm going to assume that the tree decomposition is a binary tree. Okay. Any questions? How much time do I have? Okay, so here is the property that we actually need out of this whole business of tree decomposition. So the property, I call it the separator property, is the following, that if I look at the tree decomposition, and let's say I look at this bag, and imagine that I take out all the vertices that are inside this bag out of my graph. So I just remove these guys. Then everything that is in the, let's say, everything that is in the children of this particular bag, all these nodes would be disconnected in the original graph. So in some sense, this bag forms a separator for vertices that are lying in bags that are children of this particular bag. Okay? So that's the separator property of a tree decomposition, and that's extremely useful. Yeah? So for example, if I look at these two green guys, then it's very easy to see that these three vertices, they form a vertex separator for these two, right? There is no way that you can reach from this green to that green without hitting any one of them, right? So if you remove this back, then you essentially disconnect these two. Okay, so that's the separator property, and now. Okay, now let's go back to the original problem at hand, which is Group Steiner Tree. But before going into Group Steiner Tree, let me now show you how to use these notions of tree decomposition and separators to design a dynamic programming to solve the Steiner tree problem. Okay, and that will sort of also motivate the Group Steiner problem. So let's do a DP. So as a warm-up, let's do a DP idea for the Steiner tree. So just to recap, what is the Steiner tree problem? I have this input graph, yeah, and I'm assuming that I have a nice tree decomposition of this graph, which I'm not showing in this picture, but this is really the original graph. And these green vertices are my terminals, right? And let's say that is the optimal Steiner tree, which I'm after. So this is the one which I need to find by hook or crook, okay? And now I am going to use my tree decomposition in a certain way. So let's sort of project a particular bag on this optimal Steiner tree. Yeah. So let's visualize one bag on this green Steiner tree which I have in my graph. Yeah. So let's say that it contains these 4 vertices. So how does a DP work? Well, remember, when I want to write a DP, I want to solve certain subproblems at each level in some sense, right? So now I ask the following question: what is the subproblem that I want to solve at this level of the DP? Or inside this bag, what is the subproblem that I should solve so that eventually it helps me to build this entire green structure? This is the question I want to ask. Okay? And here is one possible answer. I want to find the cheapest possible way of connecting some of the nodes in this bag. Okay? I don't know whether I want to connect all these nodes inside this bag, but I want to maybe connect some of the nodes. So that's the subproblem which I want to solve. So I tell this subproblem that, hey, you need to connect these guys with each other in the cheapest possible way. Solve this subproblem for me. And the hope is that if I can do that for different parts of my graph, then I will end up having a Steiner tree. Okay? Now, the point is, there are three ways of ensuring. So let's assume for simplicity that I really want to connect all these four inside this bag. Yeah, they are all part of the Steiner tree, and I want to ensure that they are all connected with each other. So there are three possible ways that I can achieve this. Way number one is, let's say for these two, I really buy this edge inside this bag itself. Okay, that's one possibility. But I have two other possibilities. I can delegate some of the tasks to the children bags. Remember, this is a tree decomposition, right? So imagine that there are bags also deeper down the tree. So I can delegate some of the tasks to my descendant nodes, and I can assume that some of the connections would be implemented by my ancestors. Yeah. So those are the three things that I can essentially do inside this bag. So again, just to recap, so this is the subproblem that I want to solve, but I assume that these two will be connected by something which is up in the tree. These will be connected somewhere down the tree, and this is the edge that I am going to buy at this particular bag. Yeah. Now, okay. So let's now try to summarize in the form of a DP table. So how does my DP table really look like? Well, remember, every DP table can be described in terms of some cells. So every cell, I claim, will have the following three parameters. So the first parameter is which bag am I at? Yeah. So that, let's say, XT denotes that bag. And then, remember, I have guessed some connections that could be implemented at the ancestor nodes. So I will come to how to get rid of this guess business. Okay? So, but just stay with me for a while. So let's say I have guessed some of the connections that will be implemented in the ancestor nodes. And I also look at what I need to implement and what has been already implemented in the lower level subproblem. So those are the three possible parameters that every subproblem will be characterized with. Yeah. So let's now try to figure out what would be the size of the DP table if I keep these three as my parameter. Well, the total number of bags is order n. Yeah. So this I did not mention, but yeah, the total number of nodes in the tree decomposition is order n. So sorry, I forgot to mention that. Well, the second point is the guess of the, I have a guess for the connections that will be implemented at a parent node, okay? But I claim that the total number of such guesses is not too much. It's only 2 to the power of w log w. In fact, I have written this in a fancy way. This is actually w to the power of w, okay? And why is that? Because remember, I am only trying to implement the connection inside these bags, right? And how many vertices are there inside this bag? Well, it's w, because that's roughly the Treewidth. Well, it's ordered w. Yeah. And now I essentially, if you think about connections, then those connections are nothing but a bunch of clicks among themselves, right? So w to the w is the total number of possible clicks that can happen, and total collection of clicks that can happen. And so the total number of possible guesses is roughly w to the w. Yeah. So that's another parameter, and a very similar argument can be also made for the subproblem that I am trying to solve, among the descendants. So that's like another w to the w. So the total size of the DP table is nothing but n times this number. Okay? Yeah. So any questions here? Yeah.
Why is this not 2 per w square? Because for w vertices you could have
That's a very good question. So you are saying that why isn't this 2 to the power of WC2? Yes, exactly. Yeah, that's because, remember, I am talking about connections. So when I talk about connections, if you think about 3 vertices or 4 vertices, all you want is a tree out of this vertex. You do not really need to connect each of them with each other. I mean, you do not need those many edges, right? You just need a tree. So if you think about it, the total number of forests that you can make is W to the W. That's a very good question. We initially had a runtime which was 2 to the W square, but then we made this simple observation that you can just do it. Yeah. Any other questions? Okay. So great so far. I mean, I have a DP table, but so far I have not seemed to be done anything. I have just created some weird DP table. But how do I ensure that when I solve this dynamic program, I indeed have a Steiner tree at the end? Okay. So in order to do that, let's try to visualize the DP table in the form of a graph. Okay? I define the graph in the following way. So each of these rectangles, imagine they represent one subproblem, which I described. Yeah. So they define a subproblem, and assume that this is the subproblem that I am. This blue guy is a subproblem at a specific node, and all these three subproblems pertain to the children back of this particular blue guy. Yeah. Again, remember each subproblem belongs to one particular bag, right? But each bag can have several subproblems at its level. But let's say that there is, so this is like the parent bag, and these subproblems correspond to the children bag of my tree decomposition. Now I add an edge among certain parent-children node, and here is when I do that. Remember what am I trying to do here? What is my promise at this subproblem? Well, the promise is I will implement some connections. Some connections will be bought inside this subproblem itself. Well, I just buy the edges. But remember, there were two other types of promises that I made. I promised that something will be implemented below and something will be implemented above. And now I just check that which pair are consistent in terms of those promises. So what I mean by that is, whatever I had promised to implement below at this particular subproblem, they are actually implemented by a combination of these three subproblems. And the other direction is also true. Whatever I had assumed would be implemented, let's say whatever I had assumed here would be implemented at the ancestor is actually implemented at this blue subproblem. Yeah? If that is the case, then I put an edge between those two. So I can just visualize this entire DP process in terms of this graph. Yeah? And we call this the local consistency rule. And here is the main lemma, according to me, on the paper, that if you are consistent locally, then you can actually ensure global connectivity. And this can actually be proved using very simple properties of tree decomposition. Okay? So let me just spell this out in simpler words. What is meant by global connectivity? Well, it means the following: that let's say that this blue thing, it represents one run of my entire dynamic program. Okay? So I am just hitting these subproblems in the course of running my DP. Yeah? And let's say I had promised to make some connections inside this particular subproblem. So the lemma proves that if you have made a promise here, then by the time you reach the root subproblem, you must have bought enough edges to connect these two guys with each other. Okay? That is what I mean by global connectivity in some sense. Okay? Any questions? So, given that I have this lemma, now it's actually quite straightforward to ensure that my my terminals are connected to the root, which is as follows. Okay? I promise this is the most colorful slide in my presentation. So, okay. So here is what we do. Here is a trick that I do. So remember, what I said in the previous slide is, if I have promised some connection here, that will be implemented till I reach the root. So what I do is, essentially, I promise a connection between the root and each of the terminal at certain subproblems. Yeah? And remember, every vertex has to be, every terminal will appear in some subproblem because it's part of some bag. So the only trick that I do here is, I introduce the root at every bag in my tree decomposition. And this is fine. This does not violate the tree decomposition properties. You can check. But now, essentially, if I, let's say, look at the purple terminal, then it appears in both these subproblems. And let's say I introduce the root to this subproblem, and I promise a connection between the purple guy and the root. So by the previous lemma, I know that by the time I have reached this root, they will be connected to each other. So the root will be connected to this purple guy. Okay? So that's the visualization of the entire DP process. Okay. But now the question is, why I'm doing all this business? Okay, I could have just run the DP and could have gone ahead. But here is what I claim that. I claim that I do not need to actually now solve the dynamic problem explicitly. Okay? Rather, what I could do is, I have this graph, and all I need to find is this particular tree in this graph. Okay? So I need to find a tree that has a root, and it hits at least one vertex of every color it hits one box which has like every color. Yeah. So let's say if I think about the purple guy, that's a terminal. So the covering problem that I want to solve is give me a tree such that I include one box in my tree that contains purple, include one box in the tree that contains red, include one box in this tree which contains a green, and so on and so forth. And if I can ensure that, then this tree exactly corresponds to solving the dynamic program and outputting a Steiner tree. Okay? Okay, but this problem sounds sort of familiar, right? This is what we started off with. I have a graph and I want to find a tree that connects a bunch of terminals, connects a bunch of groups to the root. So think about these two to be a group. Why are these two a group? Because both of them are colored purple. Think about these two as a group. Why? Because, or rather these four as a group, because all of them contain red. So essentially, we are again back to the Group Steiner Tree problem, right? I mean, if I can solve the Group Steiner Tree problem on this graph, then I'm done. But then we are going in circles. Well, not. So yeah, the bad news is that if I have to take this approach, I have to solve the GST problem. But the good news is that the DB graph is actually a tree. Okay, so I will not go into the details of that, but this dynamic program graph which I have been showing, this can actually be folded into a tree which is of size roughly n to the power of order Treewidth. Okay, so now I just solve the GST problem with these as my terminal nodes on a tree graph using the GKR problem. Yeah, remember GKR gives me a log n times log h approximation on the tree graph. So yeah. So if you just apply GKR rounding on sort of this huge blown up tree, then you get a log n log h approximation to your original problem. Okay. Now, one thing, if I've been able to do a reasonable job, then what you might notice is, although I describe this entire thing in terms of just Steiner trees, I have not used any special properties that it's a Steiner tree problem. This entire thing just works as it is, even if the original problem is a Group Steiner problem as well. Because, eventually I just need to say that, hey, just, connect at least one box belonging to each color class. That's it. Yeah.
So what are the edge weights in this new?
Yeah, I was going to sweep it under the rug. So the edge weight in this tree, the way we build the tree, would be the total cost of edges that I'm going to buy. And yeah, there would be like W to the W children from particular node, and each of them will correspond to the total cost of the forest that I am buying inside this bag. Okay, so let's just wrap up. So we give a log n times log h approximation for Group Steiner tree that runs in time into the power of roughly order W. So I'm hiding a log factor here. And this is the first log square n approximation for bounded Treewidth graphs. So yeah, if W is a constant, then result will follow in time. Yeah, so an important extension to this is that this entire thing goes through even if we have weights on the nodes instead of the edges. Okay, so remember our initial assumption was that the input graph is an edge-weighted graph, but this entire machinery just goes through with a few technical changes, even if the weights are on the nodes of the graph. Okay, and this is indeed nice. Why? Because there was no result known for node-weighted graphs in the general case. So there was a polylog approximation known for tree graphs, but it was not known for general graphs, and the reason is that this metric tree embedding, it does not work if you have weights on the nodes. It only works if it's a real metric on the edges, right? So the Bartal style embedding will not work in this case. However, our kind of embedding, it does not have any such requirements. Okay, so let me conclude with this final result, where we solve a more general version of the problem. So remember, so far we only talked about the Steiner tree problem, but there are a class of problems which are known as survivable network design, where instead of like one path from every terminal to the root, let's say you want k edge disjoint paths from every terminal to the root. So this is just to ensure that your network is fault resilient or things like that. So you can also define the same problem in terms of, in the context of Group Steiner trees. So our result is again a log n times log h approximation, but now the running time has two things in the exponent. So the tree width will also, of course, be there because it was already there previously, but we also have this k. So k is the total number of paths that you want between your groups and the root. So that k also shows up, and in fact, it's an open question that can you get the k outside? Okay, let me go to that when I talk about open questions. However, the upshot is that this is the first polylog approximation for any class of graphs other than trees for this problem, and k greater than 2. So let's say if k is a small constant, let's say 3 or 4, then this is a polynomial type approximation. Okay, so let me conclude with two open questions. So one question which I think is really interesting at this point is, can I get an FPT log square n approximation for Group Steiner trees? Remember, our running time is n to the power of order w. So the question is, can you pull out the w from the exponent? And can you prove a runtime of function of w times poly n or something like that? Yeah. So that's, I think, the immediate open question. But of course, the big question is, how about general graph? So what is the right answer? Can I prove a lower bound of log cube, or is there an upper bound of log square? So yeah, we continue. Thanks.
Questions?
Yes.
Think about this slide when you talked about the size of the tree.
Oh yeah.
Why are you doing such a fun? Do the nodes include all these states of the tree?
Yes.
Then why is it not 2 bar w log w into n? Why is it?
No, because remember, so that would be the size. So you are asking that, why isn't this the size of my tree? This is the size of this graph, but this graph is not a tree. This is something like a DAG if you want to. But if I want to unfold it into a tree, then I have to make several copies of each guy. For example, whenever you have nodes coming from